Oh, good day! Today we're going to tackle about digital communication techniques. This topic covers the digital transmission of data, parallel and serial transmission, data conversion, pulse modulation, and digital signal processing. So, digital transmission of data. Since the mid-1970s, digital methods of transmitting data have slowly replaced analog. Radio communication has remained primarily analog because the type of information to be conveyed is analog and because of the high frequencies involved. Today, digital circuits are fast enough to handle the processing of radio signals. Digital processing is more cost-effective and practical. Data, it refers to information to be communicated. Data is in digital form if it comes from a computer. If analog, it can be converted into digital form before it is transmitted. Digital communications was initially limited to the transmission of data between computers. Networks are formed to support communication between computers. There are three primary reasons for the growth of digital communication systems. First is increased use of computers has made it necessary to find a way for computers to communicate and exchange data. Some common examples of computer data communication include file transfer, electronic mail or email, computer peripheral links, internet access, and local area networks are also known as LANs. So there are also non-computer uses of digital communications. Among the non-computer applications of digital techniques are TV remote control, garage door opener, carrier current controls, radio control of models, and remote keyless entry. So, the second primary reason for the growth of digital communication systems is the digital transmission methods offer some major benefits over analog communication techniques. So, the benefits of digital communication is noise immunity. Digital signals, which are usually binary, are more immune to noise than analog signals. Second one, error detection and correction. With digital communication, transmission errors can usually be detected and corrected. Third is compatibility with time division multiplexing. Digital data communication is adaptable to time division multiplexing schemes. Multiplexing is the process of transmitting two or more signals simultaneously on a single channel. Digital ICs. Digital ICs are smaller and easier to make than linear ICs, so therefore can be more complex and provide greater processing capability. Digital Signal Processing, or DSP. DSP is the processing of analog signals by digital methods. This involves converting an analog signal to digital and then processing with a fast digital computer. While processing, it means filtering, equalization, phase shifting, mixing, and other traditionally analog methods. There are also disadvantages of digital communication. Considerable bandwidth size is required by a digital signal, and digital communication circuits are usually more complex than analog circuits.
So, there are two ways to move binary bits from one place to another. Transmit all bits of word simultaneously, or parallel transfer, or send only one bit at a time. Let's take this simple analogy. For example, we have a jar of candies, and we transfer them to another jar, all at the same time. Now that's what we call parallel transfer. Parallel transfer or parallel data transmission is extremely fast because all the bits of the data word are transferred simultaneously. Parallel data transmission is impractical for long distance communication because of cost and signal attenuation. For serial transfer, we only transfer one candy at a time. Data transfers in communication systems are made serially. Each bit of word is transmitted one after another. For example, the least significant bit or the LSB is transmitted first and the most significant bit or the MSB is the last. Each bit is transferred for a fixed interval of time t. Now we have serial and parallel conversion. Because both parallel and serial transmission occur in computers and other equipment, there must be techniques for converting between parallel and serial and vice versa. Such data conversions are usually taken care of by shift registers, sequential logic circuits made up of a number of flip-flops connected in cascade. The flip-flops in a shift register can store a multi-bit binary word usually loaded in parallel into the transmitting register. When a clock pulse is applied to the flip-flops, the bits of the word are shifted from one flip-flop to another in sequence. The last right-hand flip-flop in transmitting register stores each bit in sequence, as shifted out. The serial data word is transmitted over the communication link and is received by another shift register. Serial data can typically be transmitted faster over long distances than parallel data. Serial buses are now replacing parallel buses in computer storage system and telecommunication equipment where very high speeds are required. Serial to parallel and parallel to serial data conversion circuits are also referred to as serializers. The serializers are SERDES. The delta modulator looks at a sample of the analog input signal, compares it to a previous sample, and then transmits a 0 or a 1 of the sample is less than or more than the previous sample.
So now we'll go to data conversion. The key to digital communication is to convert data in an analog form into digital form. Once in digital form, the data can be processed or stored. Data must usually be reconverted to analog form for final consumption by the user. Basically, we have two conversions. First is translating an analog signal into a digital signal called analog to digital conversion, or digitizing a signal, or encoding. Obviously, the device used to perform this translation is known as an analog to digital converter, or ADC. Second one is translating a digital signal into an analog signal called digital to analog conversion. The circuit used to perform this is called digital to analog converter, or DAC, or a decoder. In analog signal, an analog signal is a smooth or continuous voltage or current variation. Through A to D conversion, these continuously variable signals are changed into a series of binary numbers which represents the digital data. A to D conversion is a process of sampling or measuring the analog signal at regular time intervals. To retain the high-frequency information in the analog signal, a sufficient number of samples must be taken to adequately represent the waveform. The minimum sampling frequency is twice the highest analog frequency content of the signal. This minimum sampling frequency is also known as Nyquist frequency. In practice, the sampling rate is much higher, typically 2.5 to 3 times more than the Nyquist minimum. So now, I have an example here of A to D conversion, wherein our analog input is a microphone, and when we plug it to a computer, we'll have now A to D conversion. So, one example of analog signal is that the microphone, the voice that we input in it, then it is automatically converted to a digital when it is transmitted into the computer. The analog signal converted into digital becomes digits or binary numbers. So we can see it through this picture. Then the analog signal represents an infinite number of actual voltage values. The A to D converter can represent only a finite number of voltage values over a specific range. So as we can see, the samples are converted to a binary number whose value is close to the actual sample value. An A to D converter divides a voltage range into discrete increments, each of which is represented by a binary number like I said earlier. The analog voltage measured during the sampling process is assigned to the increment of voltage closest to it. Errors associated with this process are known as quantizing errors. This figure shows a digital to analog converter which produces a step approximation of the original signal. The x-axis is represented by time and the y-axis is represented by the analog voltage, which is 0, 1, 2, 3, 4, and its corresponding binary equivalent, which is 0, 0, 0, 0, 0, 0, 1 for 1, 0, 0, 1, 0 for 2, 0, 0, 1, 1 for 3, and so on and so forth. The sound waves or the waveforms are the continuous analog signals, and the green lines are the stair-step approximation of analog signal. The spaces between the broken lines are the time intervals. We have an example here which is 11.7 voltage, 11.7 volts. But before that, we should know that computers are programmed to round off only once. If it's programmed to round up, then it will only round up, even if it's in 11.1. If it's programmed to round up, then it will become 12. This is called round off to This is called round off to ceiling. If it's programmed to round down, if it's 11.9, then it will eventually go to 11 even it's in point 0.9 because it's programmed to round down. This is called round off the floor. So rounding off, depending on what is programmed to the computer, we could know the binary equivalent of an analog voltage. So this is how it works. The given here is 11.7 volts. So if it's round off to ceiling, then we'll have a binary equivalent of 1100. But if it's round off to floor, then we can have a result of 1011 because it's round down. We're going to round down. That's all. That's all. Aliasing. If the sampling frequency is not high enough, aliasing occurs. Aliasing causes a new signal near the original to be created. This signal has a frequency of Fs minus Fm. When the sampled signal is converted back to analog by a D to A converter, the output will be the alias, not the original signal. To eliminate this problem, a low-pass filter called an anti-aliasing filter is usually placed between the modulating signal source and the A to D converter input. The anti-aliasing filter ensures that no signal with a frequency greater than one-half the sampling frequency is passed. This filter must have extremely good selectivity. There are many ways to convert digital codes to proportional analog voltages. The most popular methods are R-2R string weighted current source converters. An R-2R converter consists of four major sections. First is reference regulator. The reference voltage regulator, a Zener diode, receives the DC supply voltage as an input and translates it into highly precise reference voltage. Second is resistor networks. The voltage from the reference is applied to the resistor network, which converts it into a current proportional to the binary input. Output amplifiers. The output of the resistive network is connected to the summing junction of the operating amplifiers. The output of the operating amplifier is equal to the output current of the resistor network multiplied by the feedback resistor value. Electronic switches. The resistor network is modified by a set of electronic switches that can be either current or voltage switches. They are usually implemented with diodes or transistors. String digital to analog converter is made up of a series string of equal value resistors forming as a voltage divider. This voltage divider divides the input reference voltage into equal steps of voltage proportional to the binary input. The output voltage is determined by a set of enhancement mode MOSFET switches controlled by a standard binary decoder.
A popular configuration for very high-speed DACs is the weighted current source DAC. The current sources supply a fixed current that is determined by the external reference voltage. Each current source supplies a binary weighted value of 1, 1/2, 1/4, 1/8, and etc. The current sources are made up of some combination of resistors, MOSFETs, or in some cases, bipolar transistors. The switches are usually fast enhancement mode MOSFETs, but bipolar transistors are used in some models. The parallel binary input is usually stored in an input register, and the register outputs turn the switches off and on as dictated by the binary value. The current source outputs are added at the summing junction of an op-amp. The output voltage is equals to VO is equals to IT times RF. We have three important specifications that is associated with digital and analog converters. The first one is resolution, the second one is error, and the third one is settling time. Resolution is the smallest increment of voltage that the DA converter produces over its output voltage range, while error is expressed as a percentage of the maximum or the full-scale output voltage, which is the reference voltage value. The settling time is the amount of time it takes for the output voltage of the DA converter to stabilize to within a specific voltage range after a change in binary input. AD conversion or analog to digital conversion begins with sampling, which is carried out by sample and hold circuit. What is a sample and hold circuit? Sample and hold circuit takes a precise measurement of the analog voltage at specified intervals. The AD converter then converts this instantaneous value of voltage and translates it to a binary number. A sample and hold circuit, also called a track and store circuit, accepts the analog input signal and passes it through unchanged during its sampling mode. In the hold mode, the amplifier remembers or memorizes a particular voltage level at the instant of sampling. The output of the S&H amplifier is a fixed DC level whose amplitude is the value of the sampling time. The primary benefit of an SH amplifier is that it stores the analog voltage during the sampling interval. In some high-frequency signals, the analog voltage may change during the sampling interval. This is undesirable because it introduces aperture error, and the SH amplifier stores the voltage on the capacitor. With the voltage constant during the sampling interval, the quantizing is accurate. There are common ways to translate an analog voltage to a binary number include successive approximations converters, flash converter, and the pipeline converters. The successive approximation converters, um, this converter contains an 8-bit successive approximation register, or the SAR. The clock input signal sets the rate of turning the bits off and on. Successive approximations converters are fast and consistent. Special logic in the register causes each bit to be turned on one at a time from MSB to LSB until the closest binary value is stored in the register. A flash converter uses a large resistive voltage divider and multiple analog comparators. The number of comparators is equal to 2 raised to n minus 1, where n is the number of desired output bits. Pipeline converters is one that uses two or more low-resolution flash converters to achieve higher speed and higher resolution than successive approximations converters but less than a full flash converter.
Our next topic is all about pulse modulation. Pulse modulation is the process of changing a binary pulse signal to represent the information to be transmitted. The primary benefits of transmitting information by binary techniques are noise tolerance and ability to generate a degraded signal. There are four basic forms of pulse modulation. 1. amplitude modulation, PAM, 2. Pulse width modulation or PWM, 3. Pulse position modulation or PPM, 4. Pulse code modulation or PCM. So how do we compare pulse modulation methods? The PAM signal is a series of constant width pulses whose amplitudes vary in accordance with the analog signal, while the PWM signal is binary in amplitude and has only two levels. The information signal varies with the width or time duration of the pulse. In PPM, the pulses change position according to the amplitude of the analog signal. Of the four types of pulse modulation, PAM is the simplest and least expensive to implement. Pulse code modulation. The most widely used technique for digitizing information signals for electronic data transmission is pulse code modulation or PCM. PCM signals are serial digital data. There are two ways to generate. Use an S to H circuit and traditional A to D converter to sample and convert the analog signal into a sequence of binary words, convert the parallel binary words into serial form, and transmit the data serially. Second, use a delta modulator. In traditional PCM, the analog signal is sampled and converted into a sequence of parallel binary words by an A to D converter. The parallel binary output is converted into a serial signal by a shift register. Each time a sample is taken, an 8-bit word is generated by the A to D converter. This word must be transmitted serially before another sample is taken and another word is generated. The clock and start conversion signals are synchronized so that the resulting output signal is a continuous train of binary words. Companding and codecs and vocoders. Companding is a process of signal compression and expansion that is used to overcome problems of distortion and noise in the transmission of audio signals. Companding is the most common means of overcoming the problems of quantizing error and noise. All A to D and D to A conversion and related functions, as well as companding, are taken care of by a single large-scale IC chip known as a codec or vocoder. The basis of DSP. Digital Signal Processing or DSP is the use of a fast digital computer to perform processing on digital signals. Any digital computer with sufficient speed and memory can be used for DSP. An analog signal to be processed is fed to an analog to digital converter, where it is converted into a series of binary numbers and stored in a read-write random access memory, or also known as RAM. A program, usually stored in a read-only memory or ROM, performs mathematical and other manipulations on the data. Most digital processing involves complex mathematical algorithms that are executed in real time. The processing results in another set of data words which are also stored in RAM. They can be used in digital form or fed to a digital to analog converter. Most computers and microprocessors use an organization known as the von Neumann architecture. Physicist John von Neumann created the stored program concept that is the basis of operation of all digital computers. The key feature of the von Neumann arrangement is that both instructions and data are stored in a common memory space. There is only one path between the memory and the CPU, and therefore, only one data or instruction word can be accessed at a time. DSP microprocessors work in a similar way, but they use a variation called the Harvard architecture. In the Harvard architecture microprocessor, there are two memories, a program or instruction memory, usually a ROM, and the data memory, which is a RAM. There are two data paths into and out of the CPU between the memories. Because both instructions and data can be accessed simultaneously, very high-speed operation is possible. The most common DSP application is filtering. A DSP processor can perform bandpass, low-pass, high-pass, and band-reject filter operation. Data compression is a process that reduces the number of binary words needed to represent a given analog signal. Spectrum analysis is the process of examining a signal to determine its frequent content. Signal averaging is the process of sampling a recurring analog signal transmitted in the presence of noise.